I'm Rafal. I came from Poland. I'm super happy to be here. And today I will tell you about caching, especially about caching in the microservice world. But first, a few words about myself. So I'm a cloud software engineer at Hazelcast. Before I worked for Google and CERN. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and trainings, but that is not my main job. So sorry if anything goes wrong. You can say I'm not professional speaker, I'm developer. A few words about Hazelcast. Hazelcast is a distributed company. It's distributed in two meanings. First meaning is because we produce distributed software. And the second meaning is because we all work remotely. We are about 40 engineers located all over the world. We have a few people also in Russia. So it's like a big family, but located all over the world. And we have like 3 products. They are all open source. First one is Hazelcast. It is something we called caching on steroids, because in fact it's not only caching, also it's a library for a lot of things. Like generally it's called in-memory data grid, but you can do some data processing and so on. The second product is Hazelcast Jet, which is a library for stream processing. And the third one is brand new, it's Hazelcast Cloud, meaning Hazelcast put as a service in the cloud. Our agenda for today is very simple. We'll have a short introduction about caching in general, and then we will walk through all possible patterns that you can use in your microservice system. While I'm talking, I would like you to think about 2 things. First one is, which of this pattern do you use in your system? Because you need to use one of them, because this list is complete. And the second thing is, does it make sense for me to change to any other? Because that's also the purpose of this talk, to see, does it make sense to use any other of these patterns for my system? So let's start. So why do we use caching in general? So we use it for 2 purposes. The first one is obvious. It's for performance, to decrease the latency. So there is a call to our microservice, and we would like to we do some processing, and we don't want to do the same processing for the same parameters, so we cache the request response. The second one is resilience. It may be a little less obvious. So you can think that your service may be down, but I can still provide the cached value, and maybe the user will not even realize. It's not for all services, but for example, like Amazon recommendation service, which is displayed on your site. If you as a user get a cached value, it may be not completely up to date, but it's still relevant. You may not even realize that the service is down. How does it move to the microservice system? So here is a classic microservice architecture. So we have services, they have versions, they are written in different programming languages, and they use each other. And now the question is, where do we put the caching layer? Should it be inside of each service? Or should it be a separate unit in our architecture? Or maybe put them in front of each service? And that is what this talk is about. So the first architecture pattern is embedded cache. So this is the simplest thing you can imagine. You use a library which is inside your application. It looks as follows. A request goes to the load balancer. Load balancer forwards this request to one of the application web services. Then the application inside uses as a library for caching. It asks the cache, do I already have such a request? If yes, return the response. If no, do some processing, put it into the cache, and return the response. This thing that is cached, this long-lasting computation, is some business logic. It can be anything. It can be called to external service. It can be called to the database. Whatever takes time. This logic is so simple that we could even write a code for this. So in Java, if you happen to use Java, then it would look something like this. So a request goes to our system, goes to the method. We check it into the cache. If there is a cached value, we return the cached value. If no, we do some processing, put it into cache, and return the response. So you could write the code like this, include it into your application, but better not do it. Don't write your own version of caching, because Java collection or any language collection is actually not a cache. It's not a cache because it doesn't have like eviction policies, no max size limit, no statistics, no built-in cache loaders, no expiration time, no notification mechanism. So it's just not good enough for us. You're way better off by using some library. And if you're in Java, a very good library for simple caching is Guava Cache, where you can specify all these parameters upfront while creating the cache. And then use this library for caching everywhere. Another good solution for Java is EHCache. If you don't use Java for any programming language, you will find a library which provides simple embedded caching. We could even move this caching one level higher and don't always write this code, which we've just seen, but put it in the application layer. So if you use Spring, probably you will use it this way. So by specifying the annotation cacheable, it automatically does the code we written before. So the call to this method will first check if the given ISBN is inside the cache and return the cached value if it is there. If not, only if it's not, we will go to the function find book in the slow source. But be careful, because Spring, for some reason, uses concurrent hash map by default. So you are better off changing this right away. This is the first thing you start. You would like to write cacheable in your Spring application. The first thing, define your own cache manager and, for example, use Guava. So we are in this diagram. Now, there is the simple embedded caching. So there is one problem with that. Imagine that the request goes to the load balancer, and the first time it goes to the application on the top. We do some long processing, put the value into the cache, return the response, everything is fine. However, next time, the same request can be load balanced to the application at the bottom. And then we have to repeat the same operation because these caches are completely separate. So one improvement to this architecture is actually to use embedded distributed cache. It's still the same pattern, the same in the terms of application. However, this time the caches will form one consistent distributed cache. For this we can use Hazelcast. I'm not only saying this because I work in Hazelcast, but it's actually for Java applications a very good solution for embedded distributed cache. So this time the flow is the same. Request is forwarded to one of the application web services. However, these embedded caches, they form one consistent cache. How to use it in an application, in Java application? If we stick to the Spring, all you have to do is to define the caching manager, the Hazelcast as a cache manager. So let's see a very short demo on that, how to do it in your application. So here I have like a very simple Spring Web application which actually does nothing more than starts the application. And here I define exactly the same cache manager as I did on the slide. So if I start this application, first instance. We have to wait because after all it's Java, so startup time, it's slow. But it will come with the, Graal VM and all the hipster stuff. It will be faster. Okay, so we have the first application web service. It formed already a cluster which has one member. Then let me start another one. If I start another one, again it starts. But what we should see is it automatically joins the other one and forms one caching cluster. And you see it here. If I start, obviously I start more, they will all join one cache cluster. And it is consistent, so we don't have any eventual consistent, it's a strict consistency here. Now, let me stop this and come back to the slides. And it looks very easy, like they just formed one cluster together. And you may wonder how it's possible that they found themselves. So this was easy because it was run on my laptop. So by default, they use multicast. However, multicast is no good in the modern world because you cannot run multicast everywhere. So we came with the idea how to form the discovery in different environments and came up with the idea of plugins. So Hazelcast is open for discovery plugins. You can even write your own. We provide a lot of them. Actually, most of them are written by the community because Hazelcast is open source. And the idea is that you have some environment, you just specify, I would like to use Kubernetes plugin. And then for the whole discovery, for forming the cluster, it will use Kubernetes API to find another members. So you don't even have to think about it so much. You just know my execution environment is Kubernetes. So I will use Kubernetes plugin, and then the cluster forms automatically. How to use each of these plugins? It's very simple, but we published blog posts on that. So just you can reference to the blog post. If the plugin does not exist, you can always use Eureka. So one of our plugins is Eureka. Then you set up first Eureka service registry and then use Eureka for Hazelcast discovery. And it's very common for Spring applications. We ended up with the diagram like this, and that's all about embedded caching. So let's see some pros and cons of the embedded cache solution. So from the good sides, so configuration is super simple. The cache goes together with our application, so nothing can be better. The same with latency. Cache is inside our application, so it's in Java it's the same JVM, so nothing can be better in terms of latency. And we don't need any ops team or some DevOps effort to maintain the caching layer. From the downsides, configuration is not manageable. It's not flexible because if we would like to scale up our cache, then we need to do it together with our application. So we have 3 replicas of our application. We suddenly realize we would need bigger cache, but then we have to scale it up together with the application. It's limited to JVM based, or if you use some other libraries, it's limited to your language of choice for your microservice. And the data is collocated with the applications, which may not sound like a big thing. However, like in enterprise world, usually it's a big concern in terms of the security. The next on our agenda is client server. Client server is still like this old style pattern. It looks like a database style. So again, request goes to our system, it goes to the load balancer, it's forwarded to one of the services, but this time the service uses cache client to connect to the cache server, which is deployed somewhere. What's different when we compare it to the embedded mode? So the first thing is different is this part, obviously. we have something new in our architecture, so something new requires some effort to manage this. So we need some ops team. Usually in big organizations, it's managed by a separate team. Second thing that is different is this part. So this time we use a cache client library to connect to the cache server, which means that we are not longer bound to the same programming language. Like cache and client can be different programming languages. They use some well-known protocol. So, and this is a very common strategy, like for microservices. You define a caching layer, and then you can have services written in different programming languages which connect to this cache server. That is so common approach, this client server, that most caching solutions, that is the only way you can use it. Like if you use at Redis or Memcached, they only work in the client server mode, because I think Redis is written, I guess, in C, so probably you cannot embed it in your Java application, or you just cannot embed it. The same with Memcached, you always use a client server. How to run it? In case of Hazelcast, if you run it standalone, we just have a script, it forms a cluster, and then client again uses the discovery strategy plugins to connect to the server and find it. If you use Kubernetes, we provide a Helm chart. Helm chart is a package manager for Kubernetes applications. So with this one command, you can start the whole cache cluster. Then to connect to this, that would be Java code for your Spring application to connect to the server. You see that we just specify get Kubernetes config set enable true. It means it will use Kubernetes plugin to discover the cache server. So we ended up with a diagram like this. So this part, this caching part, it can be managed by a separate team. I will tell you that in big organization, it's usually managed by a separate team, even though DevOps is now popular and so on, but still if you talk to some organizations, they will use it this way. So if it's managed by a separate team, we can even move it more outside of our application and put it into the cloud. So again, the cloud is like a client server, just a very specific client server where the server part is put somewhere in the cloud, and all this effort to manage this, you don't have to do it inside your organization, but you have to pay a cloud provider to do it. How does it look like? So obviously you create a cluster in the cloud. How you connect to this cluster? That will be configuration for Hazelcast again. So you specify some discovery token which you download from the web console, cluster name and password, and that's all. So there is no static configuration here. I show you the Hazelcast configuration. However, it's not very specific to Hazelcast. Actually, almost all cloud solutions work in that way currently, that you have some discovery token to discover your cluster. No matter if it's Elastic Cloud for Elasticsearch or Mongo or whatever, they use the same way. Let me show you a very quick demo on the cloud, how to use the cloud version, and meanwhile comment on the problems we can have there. By the way, I work in the cloud team, so I need to show it because we are proud of this last hour, and it was just released, so it's super new. So first thing, you go to the cloud console. It's like web console. Any cloud thing will have a console like this. You click on create new cluster. Then you can specify the cluster name, like cluster from Siberia. Then you define the underlying cloud provider, because we don't have our infrastructure. We use the cloud infrastructure, and we did it for two reasons. So one reason, obviously, it's difficult to build your infrastructure and to make it reliable and so on. But the second thing is like, it would not be wise for us to create our own infrastructure because people will not use it. I'll tell you why people won't use it. Because people usually have their services in the cloud. Let's say that some company has their services on AWS. They also need to have the caching layer on AWS because otherwise the latency would be way worse. We are in the area of in-memory data computing, which is the area that has requirements way more strict than the databases. It really needs to be fast. If we do like on-premise client-server mode, then your cache server should be in the same local network than your application. So even like one router hop is a lot. That is why when you create this, you select the underlying cloud provider, you select the region, because you don't want your request to go to request from, I don't know, Siberia, go to the US, because latency boost would be, and you also, latency will be low, high, and you also later can set up VPC peering, so that your virtual network of your cache cluster and your application are the same virtual network. So they don't even have a router hop in between. So you select the cluster size, how much memory you need, some other parameters, and create your cluster. So it takes a moment to set up the cluster. What happens internally, we run some scripts to prepare for you your cluster. Actually, we run the same Helm chart what you've seen a moment before, because underlying how we implemented this, it's on AWS. We have a Kubernetes cluster, and on Kubernetes cluster, we run our Hazelcast clusters. And I think for 1 gigabyte, we run one Hazelcast member, so one Hazelcast node. So it's already running. If you click on the configure client, you can even, for the most common languages, you can even download the whole project. For our case, we will insert this data into the same Spring application. Let me close this. Yes, I have another config. I need to comment out the old one. So for this cloud configuration, we need cluster name. We need the cluster password. And we need the discovery token. And if I run this application now, it should connect to our cluster in the cloud. Obviously now it's not perfect because it's running from my laptop application, and the cluster is, I think, created in the US, but just for the showcase. Usually you should use the cloud version if you already use cloud for your application services. Yeah, this is connected to the cluster with this 5 gigabytes of 5 members. So coming back to the slides. Pros and cons of the client server and the cloud version. So from the good sides, we have finally data is separated from the application cache, which is usually a must for big organization at least. We have separate management, so we can scale up. We can do some auto-scaling of the caching cluster. No problem here. It's programming language agnostic because we use the client library to connect to the server. From the downsides, it requires DevOps effort to maintain the cluster or paying the cloud provider. The latency is higher because we at least need to use network. It can never be that good as the cache which is inside your application. And you need to set up what we just discussed, like really to be your cache in the same network. Okay, you may say that the first like embedded cache and client server is kind of boring stuff because it's old. Actually, I mean, cloud maybe is relatively new, but client server embedded was always there. So now something a little more interesting. So cache as a sidecar. Sidecar is a completely new idea because it's related to only container-based environment. So this time our diagram will be specific to Kubernetes because this war of the container world it's already won by Kubernetes. Everybody's using Kubernetes. So in the Kubernetes we have an maybe short introduction about Kubernetes. In Kubernetes, a deployment unit is a pod. And a pod can contain one or more containers. It usually contains actually one container with an application. However, it can contain additional containers for some purpose. For example, if you would like to redirect your logs from your application, you can inject a logging agent which will forward your logs to some logging system. And this logging agent can be deployed as an additional containers. And this additional container is called a sidecar container. So sticking with the idea, we will deploy our application together with a cache server container. This time the flow will look as follows. Request goes to the Kubernetes service, which is kind of a load balancer in the Kubernetes world. It will go then to one of the Kubernetes pod. Application will take the request. Application will use cache client to connect to the cache server. However, the cache server is always located in the same pod, so it's always deployed. Kubernetes guaranteed that all containers in the same pod are deployed on the same physical machine. So application can even use localhost to connect to the cache. And obviously all the caches, they form one caching cluster. So this solution is somehow similar to client server and somehow similar to embedded mode. It's similar to embedded because it's the same physical machine after all, it's the same resource pool, and it scales up and down together with your application. However, it's different because we use cache clients, so you can write it in any programming language you want, and there is some kind of isolation between cache and application. The isolation is on the container level. How does it look like in the code? So for the cache manager configuration, we add a static configuration to always connect to the local host. Configuration is static, but the whole system is dynamic. We just know that cache server will be always injected in the same pod, so it's always available at the local host. Kubernetes configuration for this. We have two containers in the same pod. First one is our business logic, our application web service, and the second one is always the same, it's the cache server. Pros and cons. The configuration is again very simple. It's programming language agnostic. Latency is low, it uses the network but the local network. And there is some kind of isolation between data and application, which I mean, it's on the container level, so depending on your security requirements, it may be good enough or not. From the downsides, it's limited to the container-based environment. Management is, again, not flexible, and data is physically collocated in the same pod. And our last architectural pattern for this presentation is reverse proxy. This will be something completely different. It will be different because so far, all these patterns, application knew that such thing as a service exists. So it was aware that it connects to the application. This time it will be different. We will put the cache in front of the application. So our diagram will look as follows. Request goes to our system, it goes to the load balancer, and then just in front of the load balancer or just after the load balancer, there is a caching layer. So it's at the protocol level. And only if it's not found in the cache, then it's forwarded, that is load balanced to one of the application services. A very good solution and mature for such things is Nginx, which you can configure even together with your load balancing. You can add the caching, just specifying the path to your local file system. The path to local file system, it may, we never so far defined like the path to your system, and it's somehow important because so far, like in any caching solution, we didn't use file system. Like Hazelcast even doesn't have an option to put your data into your file system, and it's done on purpose, because if you are guaranteed that the data is stored in memory, you have some guarantees about the latency, about the time. Otherwise, obviously, Nginx doesn't store all the data on the file system. It only offloads, but then you can never be sure if it was offloaded or not. And Nginx has some other problems. It's related only to HTTP level, which is probably not a big deal in the current world. But it's not distributed and it's not highly available, which is definitely a big problem. And the data, as I said, it may be stored on the disk. You can use Nginx with some plugins, which are not mature. I mean, for Hazelcast it doesn't exist yet, but for Redis it exists, but it's not very mature, so probably not good thing for production environment. If we take this idea of reverse proxy, so putting your cache in front of your service, and merge it with the idea of sidecar, we end up with the last version of the pattern, which is reverse proxy sidecar. Reverse proxy sidecar there's no major solution yet, but people are working actively on that, so this will become a big thing very soon. How it will work? So request goes to our Kubernetes service, it's load balanced to one of the pod, but this time it's not the application that gets the request, but it's something I call reverse proxy cache container. So there is a cache in front of the application which kind of intercepts the traffic, and only if it's not found in the cache, it's forwarded to the application. And if you think about the whole idea of putting your cache in front of the application, it has some good and bad sides. Let's be optimistic and start from what comes good with that. You probably remember the first diagram on this presentation. So we have a classic microservice architecture. A lot of services in different versions, in different programming languages, they all use each other. So generally a mess, like all that comes with this microservice style. Now, if you use this, now the big thing about this reverse proxy sidecar is that you don't even touch the application code to introduce the caching layer, to configure the caching layer. So you can say in a declarative manner on the configuration level, I would like to have cache in this and this service. That's all. You don't touch the code of your application. You don't have to even, compile your application, build images, whatever. So in a declarative manner, you inject the caching layer. Sticking to the Kubernetes, this would look something like this. So you have our application. Let's start maybe from the bottom this time. At the bottom, we have our application, so this doesn't change. Then we have this caching proxy, which is this kind of interceptor. But we also need to have one more image. So this one more image, init container, it's something that is run once before your pod actually starts. So this init networking, it will be a simple script that changes your networking in a way that it's not the application container that receives the requests, but all the requests coming from outside are received by reverse proxy cache container, and all the internal call on the same port goes to the application. script looks something like this. So we does the whole script of this init networking. It just changes your IP tables. If you look at this diagram again, and the whole idea of the cache injection, it may make you think about service mesh and Istio. That is the diagram from the Istio documentation. Because actually the idea is the same. I mean, Istio is doing exactly the same. It has this init networking and all this, and this additional container. Istio is currently for redirecting your traffic or introducing the security in a declarative manner, in the injection manner. And Istio is planning to introduce this cache. So as soon as they implement this GitHub issue, this will become a big thing, this reverse proxy sidecar. And you may think like this GitHub issue is old, but they are actively working on that. So they are actively working. I mean, there are pull requests to the repo open. But okay, I told you like the whole idea, it has some good things, but also it has some downsides. So if we put our caching layer in front of our services, there is one thing that becomes way more difficult. It is the cache invalidation. And if you look anywhere on the internet, what causes the most of issues with caching, everyone will tell you the same. It's invalidation, meaning when to decide that my data is in cache is already old, it's stale. I should not use the cache data, but to use the real data, to go to the database or go to the external service. And if our application is aware of the caching, we can have some business logic for this. Like in cache, we can, in Spring, we can say, okay, evict this cache value if something happens. However, if the cache is injected or it's just in front of our application, that we are stuck with the timeouts, e-tags, everything that you can use in your browser actually. So it's actually we are stuck to the timeouts, which may be good enough for your use case or not. So a short summary about reverse proxy and reverse proxy caching solutions. So from the good sides, and the main reason why you would use it is that it's configuration based, so there is no need to change your application to have caching. It's programming language agnostic. It's actually everything agnostic. It even does not touch your application. It's this solution is very consistent with the containers and microservice world. That is the direction it's all going. Like Istio is already a big thing. You can even start your on Google Cloud Platform Kubernetes cluster with Istio by just clicking a button. So they are really going into that direction. From the downsides, we already said invalidation. There is also no major solution yet. If you use just reverse proxy, then Nginx is a good solution with the problems mentioned. But if you would like to use reverse proxy sidecar, there's no solution. We implemented in Hazelcast a prototype, but definitely not something that you can use in your production environment. Istio is working on that, so that will probably come as a good solution for that. I mentioned also it's protocol based, but let's be real. I mean, now microservices, they are HTTP based almost all the time. So this was the last pattern for this presentation. So as a very short summary, I could repeat what I already said, but it would probably be boring. So what I propose is a very short decision tree, like which caching solution to use. It's oversimplified, so let me say it at the beginning. But it may at least give you the idea in which direction to follow. So the first question I would ask is, does my application need to be aware of the caching? If no, then the next question, do I use containers? If no, use reverse proxy. If yes, use reverse proxy sidecar as soon as there is a good solution for that. If my application needs to be aware about caching, then do I have a lot of data or some security restrictions? If no, then does it need to be language agnostic or is it container based? If no, use embedded distributed. If yes, use sidecar. However, if you have a lot of data or you work in a big organization, then the last question is my current deployment a cloud? If no, use on-premise client server. If yes, use the some hosted cloud version, because it will just save your money after all to use something managed that you don't have to work on. And as the last slide, I suggest a few resources. The first one is our blog post explaining how to run Hazelcast as a sidecar. Second one is this prototype I mentioned for reverse proxy sidecar, but it's very prototype, so you can play with this, but don't use it on production. Third one link is about cache break practices. It's not related to this talk, but it's a very good blog post about caching in general. And the last one is a very good video talk about how to set up Nginx as a reverse proxy caching. So with this last slide, I would like to thank you